Yeah.
This might cut off because of battery, but I don't know. It's been charging all night, so. Okay, here we go. Hopefully remember what Riemann sums look like from pre-calc. Remember your Riemann sum there? Yes, hopefully. It is a counter. This actually means sum starting here and ending here. And it's just a placeholder. So K, you'd plug in 1. Then you would plug in the next whole number, 2. Then you plug in 3. Keep going your whole numbers, and this tells you the last thing you'd plug in. And this means sum, so you just add them all up. Okay. So let's look at our rectangular approximation method here. I have just a generic function, and I separate it into rectangles. Whoa.
Whoa.
And I'm going to make my rectangles touch a different amount. I'm going to make them different sizes. It doesn't really matter. I'm just going to do random stuff here. I make one really skinny, make one really fat. Just in general, making them touch random places and random widths. So they don't have to be evenly spread apart. We saw that yesterday.
So this isn't necessarily all LRAM or all. It's just also.
I'm just doing random places that they touch. Yep, exactly. So we're going to try to write a Riemann sum for this random situation. So each rectangle, let's start some notation here. I'm going to call this width delta x1. Delta means change in your x. Okay, that's why I'm using that notation. It means the change in the x. So there's a length there. Then this one, remember they don't have to be the same width, so I'm going to call that delta x2. Delta x3, so on and so on. What would this one be? Delta x n. And this one would be delta x n minus 1. Okay. Now, they're touching at random places, so I can't use LRAM, MRAM. I just pick generic places, so we need another variable. I'm going to call wherever they touch C sub 1. So this place would be C sub 2. Here it touches here, C sub 3. C sub 4. C sub 5. All the way down to wherever that touches C sub n. Then the height of the first rectangle would be what?
C sub n. Oh, no.
Height. It would be f of C sub 1, correct? The height, because that's where it's touching. This would be f of C sub 2. So now that first rectangle, length times width, I have f of C sub 1 times the width, delta x1. You with me there? Length times width. The next rectangle would be f of C sub 2 times delta x sub 2. Plus, add up all the rectangles. And the last one would be f of C sub n times delta C sub n. You remember this notation, all of our subscripts, sums hopefully. Now I can write this as a Riemann sum because notice I have counters. 1, 2, 3, 4, all the way to n. So I can write it as a Riemann sum. So as a Riemann sum, I'm going to pick a generic variable. We're going to use k. It doesn't matter. You see i's a lot here. You see j's. It doesn't really matter what variable you choose, but I'm going to use it as a counter. So I'm going to say k is my subscript. So I would plug in 1 and get C sub 1. Then you'd plug in the next whole number, C sub 2, C sub 3, all the way until you plug in n. Okay? And this means sum. So this Riemann sum right here represents the area under that curve. By the way, when we say area under the curve, we always assume to the x-axis, correct? Entrapped by the curve and the x-axis? Yeah? Now, by definition, this is the definition of a definite integral of continuous function. We're only looking at assuming it's continuous. So if f is continuous on AB, it doesn't matter if it's capital or lowercase. Probably should be lowercase, they use it down here. And we're going to assume we're breaking it up into subintervals. And in this case, we're going to make them the same size because that's the easiest case. We could make them all generic. It doesn't matter. But this is the exact same thing we just had. We noted that this was adding up all the rectangles, correct? What does this do when I take the limit as n goes to infinity? What is that saying in regular terms? What's that doing to my picture? You're right. We're getting more and more rectangles, so they are getting infinitely smaller. So it's making it more accurate. And if we take the limit as you go to infinity, it's virtually going to be the exact area under the curve. And that's what a definite integral is. Okay? But this is the definition of a definite integral. Now, Newton and Leibniz years and years ago said, well, this notation, that's not user-friendly. Okay? It's what a definite integral means, but that is not user-friendly to write that over and over and over again. Yuck. So they came up with integral notation, which is the elongated S, which is actually what that's called. Elongated S.
Oh, yeah, here we go.
So it looks like an F without the cross.
It's on the Dasani bottle.
Okay.
Everyone look.
Yes, lovely. It's on the Dasani bottle. Thank you.
Thank you
Okay.
for your bottle.
So, we put our integral, and it does matter, the interval in order, small to big. Okay, A to B. Order does matter. This is called our integrand. The actual function is called the integrand. You do need a dx. That is saying your variable is x. You're integrating with respect to x. Okay? That matters. When you go to take multivariable diffq, you'll get some, one of my favorites are double and triple integrals.
Those sound so fun.
They are fun. They actually are. You're being sarcastic, but they are. Integrate, and then you integrate, and then you integrate again. They are fun. Those are my favorites. And when you take some of you will have to take calc statistics. Like I did not have to take regular statistics in college. I had to take calc-based statistics, which is fine because I like it way better. But use that a lot in statistics. Integrals are used in a lot of statistic applications as you get to the higher level stuff. Okay? But dx is your variable integration. Function is called the integrand. It's important to note that the integral means area under the curve. Once again, enclosed with the x-axis. So, derivative graphically means what? Slope of the tangent line. Integral means area under the curve graphically.
Cool.
Okay. There's a great project, and if we have time, maybe after the AP test, we'll do it. Did you guys do last year with beakers and water?
Last year.
See the area under the curve and how it relates to
We
the
did that
slope of
in
the
AP
tangent line?
or something like that.
No, we didn't.
We had
Anyway, you had beakers, thank you. Yes, you had beakers and water, thank you. Okay. Okay, very, very easy question. It will actually take longer to read than it is to do. Saying the interval -1 to 3 is partitioned into n subintervals of equal length. We're going to express this as an integral. That is a hot mess. We're going to write it as an integral.
Just like
Okay, so we know we're going from -1 to 3. I need to identify my function. So do you see my counter in the variable? We're just going to replace that with regular old x. Just make it a user-friendly variable like x. So I would have 3x squared minus 2x plus 5. I'm going to put it in parentheses because the last I have to have dx. You must say that, hey, my variable is x. That is actually being multiplied, which is why we have parentheses here. Sometimes you'll see people as they go along kind of drop those parentheses because they are assumed, but they need to be there. Okay, they really should be there, but they are kind of assumed. You will see it in some texts and some professors' writing. Okay. Because what is happening is actually the function times that dx. They're actually being multiplied.
Hi,
Wait,
Connor.
do we have to
Fox
do the
Lane.
U-track?
Everyone say hi to Connor.
Yeah,
Do
it
we
might,
have-
it might shut off here in a minute.
We should ask him a question.
Do we
Like I
we should
said, the
call him.
calculators are not working, so we're just gonna quickly do you try. Give you 10 seconds.
Whoa.
Whoa.
Sorry, didn't have to worry.
We're trying to get an integral for next.
It's gonna be good.
Struggle.
How we do?
Throw it down.
Pretty solid.
Pretty easy,
Better than
right?
Connor.
When you see your homework assignment tonight, you're gonna be like, oh, that's a lot of work. But some of them are this. They should not take any longer than 5 seconds to do.
Still.
Okay? That is not a lot of work.
Unless you're
Okay.
a Z.
You must have dx. It will be marked wrong if you do not have dx, dy, d theta, whatever your variable is. Okay, so
Like.
we're gonna evaluate this integral using the graph. Next chapter, we're gonna get into refreshing those integration methods, like substitution, integration by parts. I know you've seen that. I don't think you've seen partial fractions.
Oh, that's the best.
I don't think that. I don't think we did. Did we do partial fractions last year? I doubt you did. Okay. But remember, integral means area under the curve. This is a pure function. What does that graph look like?
It's a curvy line like this.
It's a curvy. There's no such thing as a curvy line.
A curvy graph.
Otherwise known as a curve.
Bodacious.
It is not that. I see a lot of you saying it's a square root. It is not.
It's a semicircle.
It's
Isn't
a semicircle of radius 2.
2.
Radius 2.
So
It is the top half of the semicircle. How do I know that?
because it's the area under the curve,
minus
which is
x squared,
assumes
so
the
it is
x-axis.
It's going down. It's a
it?
minus.
It's a square root.
Because it is a positive square root.
Absolutely.
This would be the bottom half of the semicircle, correct? Yes, no? And we can have stuff under the curve. And so I want to remind you, if the area is under the x-axis, it is negative. Okay? So if you're under the x-axis, you know it has to be negative. But here, we're now going to use geometry. We're going from negative 2, negative 2 to 2.
Yep.
Have to squeeze the trigger.
It's half a circle. So my area, 1/2 pi r squared. So in our case, 1/2 pi 2 squared, which gives me what? 2 pi.
You don't bother me.
And if that was bottom, it would be negative 2 pi. What if I gave you the integral 0 to 2?
1/4.
It would be a 4th pi r squared because you're doing a quarter of
So
a
just
circle. We're just using geometry formulas right here. Go ahead, find me the area under the curve from 1 to 3, absolute value x minus 2 dx. And by the way, homework tonight, there are a few graphs. I think there's like 4 or 5 graphs. Guess what? They need to be on graph paper.
We don't have paper.
Graph paper.
Because there is an important basketball game tonight, can we not graph them?
Yeah, JV girls.
Oh, I thought we were talking about middle school.
Yeah, me too. Does anyone want that joke explained?
About the.
Huh?
I thought you were talking about football.
Okay, we know that as an absolute value. The v moved over right to So from 1 to 3, area under the curve to the x-axis, you have two little triangles. I only found the area of 1 because it is symmetric. We can just multiply by 2 when we're all done. That's exactly what I did. 1/2 times 1 times 1. By the way, if these get complicated, some people, they don't graph perfectly. Like it doesn't go through a square nice and neat. How could you find the height?
Plug it in.
Plug it in. People forget that.
You
Okay.
goofus.
We have the function. Plug it in if you don't know for sure where the height is. But I just found the area of that to be 1/2 symmetric times by 2. We remember our formula for trapezoids, right? It happens to be one I noticed that a lot of us forget. It is the average of the bases times the height. Please use trapezoids and save yourself some time. For instance, let's say I had a graph.
Get up off my trap.
That goes through that line there. Up here, and I needed to find the area of this chunk. So many people split it into a triangle and a rectangle. Save yourself some time. That is a trapezoid on its side, correct? Yeah. No, you have to know the area of trapezoid. Anyway, we're going to do trapezoid on this. Okay, what do the graphs of constant functions look like?
Rectangle.
Well, if constant functions look like all lines are straight.
Oh,
Horizontal
roasted.
lines. Okay. So constants are horizontal lines. We're going from the interval A to B. It will always be a rectangle.
Or square.
And if I do length times width, what's the length here? B minus A. What's the height? The function, the constant. So, we do not need a graph for constants. The integral of a constant, with respect to any variable, is simply the constant times the difference in the interval, B minus A.
Can you go back to the last slide for like 2 seconds?
2 seconds.
Ready, set,
One.
go.
2.
Okay, got it.
Okay. So these should be easy peasy. Once again, these should be really quickly. So I'm only going to do 1 or 2. I have the integral of a constant. That is just the constant itself. Now order matters. B minus A. 8 minus negative 1.
Here's 4.2.
Okay. So 4 point, if you don't
37.8.
do it.
I'm signing autographs later.
There will be no line for that.
For the guy.
Okay.
For the guy
You have a
who
few
uses
homework
calculator
questions
on
just
the
like this.
calculator
Once again,
test.
they should be pretty quick.
Aggressive.
Do not draw graphs for the constants. Okay, now let's look at our rules. By the way, that was 6.2. We just covered.
That took a while.
6.2.
Alright, homework time.
Now let's look at rules for definite integrals. Once again, these are definite because I have an interval, A to B. We'll get to indefinite where you have no interval later. Okay. The integral from A to B f of x dx is equivalent to negative integral b to a f of x dx. That should make sense when we think of a picture. The integral is represented by this picture, correct?
Yep.
From B to A. This is where the definition of the integral. So if I went the other direction, A to B, I'm just subtracting the opposite direction, which will change the sign, which is why we compensate with that extra sign on the outside. The integral of A to A is 0.
True.
That should make complete sense. If I'm going from A to A, I don't have a rectangle. I don't have any area under there. There's nothing to draw. Have you guys seen that thing online about calculus can be funny if you get it? You seen that?
Oh yeah, that's it.
About the, now have you seen, do you know, really know what I'm talking
Yeah.
about?
Explain it.
No,
this is gonna come in handy when we do integration by parts and substitution. You can take the constant out, which makes the function easier sometimes to integrate. Then when you're all done, multiply by the constant in the end. Okay, very, very big rule we're gonna be using a lot there.
It's not that calculus can be understood, it's the ability of the person trying to understand it.
Oh my gosh.
And you're like the 3-year-old.
The integral from A to B, if I'm adding or subtracting two functions, I can add or subtract them individually. Okay. Pretty straightforward there. And the last one, when you draw a picture, makes sense. A little weird, otherwise you're gonna go away. Here. The integral from A to B f of x plus the integral b to c of the same function is equivalent to the integral a to c. So here's a, b, c. So if I add the integral from a to b plus the integral b to c, did I just find the integral a to c?
Yeah.
Comes together. Now, a lot of people forget that we can rearrange that. Okay? This is true. The integral from a to c f of x dx minus the integral from b to c f of x dx is equal to integral a to b f of x dx. So in other words, if I'm given this whole thing and I'm given this, I can easily find that by subtracting, correct?
Yes.
So you can rearrange this as well. Okay? These are your properties. Any other properties you don't know about. They could be true, they may not. These are the ones that are proven to be true. So let's try this. I'm given an integral, negative 1 to 1, f of x dx is 5. Don't know what the function looks like. All I know is its area under the curve from negative 1 to 1 is 5. H of x is a separate function. Its area is 7 on the same interval. Then f of x on a different interval is negative 2. Way too far. Come on.
Yes, you're nuts.
Come on. What the heck? Stop it. Stop it. What the heck is it doing right now? So the integral from 4 to 1. Well, I do. What are you doing?
This is the problem.
I'm getting rid of my. There we go. Let's try that. That is out of order. It should be A to B. So this is equivalent to negative 1 to 4 f of x dx. And what was the integral to begin with from 1 to 4? Negative. I have no idea what my computer is doing right now. Acting silly.
Not the right thing.
Okay, so negative 2 is 2. Please get in the habit of making the connection between this and this. I don't really care what number you get. Yeah, I want you to get the right answer, but that's not the important part right here. It's knowing the property that I can flip that a and b as long as I multiply by a negative. The integral of negative 1 to 4. That is equivalent to the integral of negative 1 to 1 plus the integral 1 to 4. What was the integral of negative 1 to 1? Help me out, I can't see it up there.
5.
That's 5.
5. What was that? Negative 2? So total I get 3. By the way, the fact that that area is negative 2, what does that tell you? The majority of it is under the x-axis, right?
Yes.
There could be some above, but majority of the graph is below. Let's deal with those constants. It's a very easy one to do, but I want to show you technically we're using two rules where I take out that constant and I separate the functions. Technically I'm using both the constant rule and the addition subtraction property of integrals. This was 5. What was that, 7? So I'll get 10 plus 21, which is 31.
31.
integral 0 to 1 f of x dx.
Did you do, no.
Oh, it's just two. It's 5 halves.
Is it?
No.
No,
You're not
no,
guaranteed it's that.
no.
Yeah, but you.
You are told negative 1 to 1, but how do you know it's symmetric?
You can't find it.
You don't. You can't find it. You don't have enough information. And the notation we use for that, what does NEI stand for?
Never English inbreds.
Never eat eyes. Never eat iodine.
Not
Never eat
enough
ice cream.
information. That is
Never
universally
indulge.
known, so AP graders will know that that's what you mean. You don't have information. Now, if you were told this was an even function, then yeah, you could say that's 5 halves, because evens are symmetric about the y. Okay? But you are not told that.
even interested.
No. Negative 2 to 2. H of x.
NEI.
NEI.
Yeah.
Oh.
You have no idea what's going on with h of x beyond negative 1 and 1. You cannot double it, which is what some people do. You do not know what's going on past that.
Oh wow, yeah.
NEI.
NEI. We could do this. This part of it, we have enough information from negative 1 to 4 of f of x. But here we only know negative 1 to 1. So automatically overrides an NEI.
I would get a
What does
lot
it
of
actually
those
stand
on
for?
homework.
Not enough information. By the way, I fool so many people with this.
Not even an integral.
You got it in hand there.
Not
Yeah,
even-
but you remove it.
Ooh, that's multiplication.
3/4 people miss this on a quiz or test, even when I tell them. So we are not going to do that, right?
NEI.
Wait, so
NEI.
why?
There is no property
You can't split
that
those
says
up.
you can multiply functions
Yeah.
and integrals.
Yeah.
No property exists. It is not true. It might sometimes be true depending on what function you're given by coincidence, but that is not a property of integrals. Okay? So that is not on the list. Okay.
Bill Nye the Science.
Now let's get into the meat of it. We're going to find integral values using antiderivatives. So we can find integral values using graphs, but we can also find them using antiderivatives. Now, next week on Monday, we're going to go into officially the FTC. Okay? The fundamental theorem of
Federal
calculus.
Very
Trade
time capsule.
Commission.
The most important theorem we do all year.
And a push.
It's, some would call it fundamental for
CPC.
calculus.
Good one.
I don't know. Yeah.
I see.
But this is part of it.
Oh, no,
What
that's
this
not-
is, if big F is the antiderivative of little f, you can take the antiderivative, evaluate at B, evaluate at A, subtract, and get the area under the curve without the graph. Without the graph. Order matters, it must be B minus A.
I'm a B.
I'm a-
Sorry, it was there. I had to take the chance.
Here we go. What's my antiderivative of each piece?
X to the fourth
X to
minus
the
X
fourth.
squared plus X.
Plus C.
Now, I'm not going to put a plus C, and you'll see
No,
why in
you're
a
not,
minute.
because it's not indefinite.
Okay. Here's our notation. You will often see a bracket 0 to 1. Sometimes you'll just see a very long line there, 0 to 1. Usually you'll see a bracket when it's written by hand. Once it's typed. Now, evaluate. Show me work. Plug in 1. I get 1. Minus 1. Plus 1. Plug in 0. 0 minus 0 plus 0. What do I get? 1. The area under the curve is 1. We need to be speedy with these. Maybe test will assume, after we do a bunch of these, that these are second nature. You can evaluate these and do them quickly. Okay, they will just assume that is one of the basic things. Kind of like the power rule. They will assume you can do the power rule quickly. They will assume you can do basic integrals quickly. Okay, antiderivative here.
2
2
ln
ln
x plus 1.
I'll just use parentheses for now, because we're going to evaluate. So now plug in 4, I get 2. Natural
Absolute
log of
value.
5. Is that?
Absolute value.
Well, I just said I could, but but I don't need to considering I'm plugging in positive numbers.
Glad you're listening.
Okay. Plug in 0, you get 0. Natural log of 1 is 0, correct? So I end up getting 2 natural log of 5. You might occasionally see that written as natural log of 25. Usually not. This is how you usually see it. By the way, let's go back here. Folks are wondering the reason we don't do plus C is because x plus C evaluated from 0 to 1 is an x. When I plug in 1, I would get 1 minus 1 plus 1 plus C. Plug in 0, I get 0 minus 0 plus 0 plus C. Your C will always be C minus C. Every single time.
In your face.
That's why we do not have a plus C for definite intervals. Quick, you try. Be careful. This one you might have to think about for a
Try not
second.
to be terrifying.
Couple of things. You don't have to. I like to pull my coefficients out. It doesn't really matter, but notice that the antiderivative of that would be negative e to the negative x. Got a little tiny backwards chain rule going on there. Okay, so that'll make that a negative, which is positive. Plug in 2, and plug in negative 1. Usually you will see that written as 3 over e squared. You'll see them written with positive exponents. Usually. Questions?
What is
Hopefully we'll get cut off.
No, I've got fancy.
Average or mean value is sometimes called the mean value theorem for integrals. This is literally an average. We no longer do that old school add them all up, divide by how many there are. It's not nearly as accurate as calculus average. Okay? Which is the integral times 1 over b minus a. It's sometimes called the MVT for integrals. So if you see it referred to as the MVT, it does come from the MVT. So quick, we might run out of time here. Let's find the average value. I mean, on average, it might go above the graph, it might go below. Where does it, on average, lie? So I'm going to do the integral 1 over b minus a, integral a to b, f of x dx. So in our case, it's 1 over 3 minus 0, integral 0 to 3, 4 minus x squared